Hello and welcome to another one of our online lecture videos with differential equations. Today we're going to be looking at transformations of initial value problems. So first we're going to start with a couple of identities and we're going to show this. We'd like to show that if capital F of S is equal to the Laplace transformation applied on some function little f at t, which is by definition the integral from 0 to infinity of e to the minus st times f at t dt, that improper integral we talked about last time, then we get these two following relationships, that the Laplace transform applied on f prime at t is equal to s times big F at s minus little f at 0, and the Laplace transformation applied on f double prime at t gives us s squared times capital F at s minus s times little f at 0 minus f prime at 0. Now let's see if we can show this. So first, what I want to start with is the first order derivative, the Laplace transformation. Here I'll use the script L applied on f prime at t. And we'll say, well, what is this by definition? This is the improper integral from 0 to infinity of e to the minus st times whatever my function is. In this case, it's f prime at t, so times f prime at t dt. Now to work through this, we want to use integration by parts. So here I want to make my choices for u and my choices for dv. And in order to get this to work out, I'm going to choose dv to be f prime at t. So f prime at t dt is my choice for dv, which means then u is this e to the minus st. And if I go to my choice for u, if I differentiate it with respect to t, you would say the derivative on the left, derivative of u is 1 with respect to u. That's 1 du, which is du. And over on the right-hand side, the derivative of e to the minus st with respect to t gives us e to the minus st times negative s, and that's with respect to t, so dt, and that's just chain rule, e to the stuff times the derivative of the exponent. And then to go from dv to v, I have to integrate, so the antiderivative of dv gives us v, and the antiderivative of f prime at t, right, if this is a derivative, if I integrate it, it's going to bring me back to little f at t. Now keeping in mind this is an improper integral, at some point I'm going to want to think about this in terms of a limit, but if I just go and work with my integration by parts formula right now, which is the integral of u times dv is equal to u times v minus the integral of v times du, I can start substituting some of these things in. So I'll say, okay, first I want u times v, which is e to the minus st times f at t. And this should be from 0 to infinity. And infinity is not really going to be a bound for us, so we're going to rewrite this as a limit, of course. But for now, I'll just write this so I remember what the situation is. And then minus the integral of, and this is the improper integral from 0 to infinity, so minus the integral of v times du. So that's going to be f at t is v times du is negative s e to the minus st dt. But we said infinity really shouldn't be a bound. I don't want to treat it like it's a numerical value, right? It's not a number, it's an idea, a concept, some idea that keeps us up late at night. So I do want to rewrite this. So here I'll say with u times v, I don't really have to do anything special with it. I just have to evaluate it, but no more calculus, right? Well, the limit. But we'd say limit as b goes to infinity. And here I might rewrite it as well. Say here I can write this as f at t divided by e to the st. So f at t divided by e to the st. And this is from 0 to b. And I have that limit notation in front. And then here for the integral, let me leave it as an improper integral, but let me bring this negative s out in front. So minus negative s is going to switch to plus s times the integral from 0 to infinity of, what am I left with? Well, I brought the negative s out, so I'm still left with this e to the minus st, and I'm still left with my function little f at t, dt. So this is what I'm left with. Now there's a few more things that I'd like to do with this. If I go and evaluate plugging in my upper bound and my lower bound into this u times v part, we get the limit as b goes to infinity of, if I plug b in for t, that gives me f at b divided by e to the power of sb, and then minus, if I plug 0 in for t, I get f at 0 divided by e to the power of s times 0. And then plus this integral, so I'm just going to rewrite that. So plus s times the antiderivative from 0 to infinity of e to the minus st times f at t dt. Now there's a few comments that I want to make here. This limit as b goes to infinity really only affects this first term, since that's the term that has b in it. And we could say the following. In order for this to give me some answer, so in order to get an, I'll put answer in quotations here, because the idea is we want something usable, right? Now this could diverge as b goes to infinity, and if it diverges, then this whole expression is going to be divergent anyways. And we'd say, well, okay, so if it diverges, then I do get an answer, but it's not really something usable. So in order to get an answer that I can use, and we'll sort of talk about it colloquially, we really need that little f at b goes to infinity slower than e to the power of sb. And this is colloquial, so let me put this sort of in quotations here so we can sort of think about it more than we're necessarily talking about it. The idea is that I want to be able to use some argument with L'Hopital's rule or something like that, where I can say that the function little f at b, although it is going to head to infinity, that it's not going to outpace the exponential function. And usually that's the case, right? Usually exponential functions go there faster. So we're hoping that that's the case here. And really what we're saying is we're hoping that the limit as b goes to infinity of f at b divided by e to the sb is actually 0, that this will converge. If it doesn't, then I don't really get anything usable from all of this. So it's a, well, under that assumption that this is going to converge, what do we get? Well, so then if this goes to 0, I get 0 minus, and then what about this other expression here? I have e to the 0 in the denominator, but e to the 0 is 1, so I get f at 0 divided by 1. And then I have plus s times the integral from 0 to infinity of e to the power of minus st times little f at t dt. And there's a lot that I can say about this, and we're sort of coming to a close here with this first identity. Say I don't need the 0. This minus f at 0 divided by 1, that's just minus f at 0, plus, here I have s times, we should recognize this integral. The integral from 0 to infinity of e to the minus st times little f at t, that is by definition the Laplace transformation of little f at t. If I go back here, we said at the very beginning, Laplace transformation on little f at t is the integral, the improper integral from 0 to infinity of e to the minus st times little f at t dt. And I have the expression right in my answer. So this is negative little f at 0 plus s times the Laplace transformation of little f at t. And now I can just clean this up a little bit better to write this as a final answer. So I would write this first. I would say s times. And in general, the Laplace transformation applied on little f at t gives us a function capital F of variable s. We can scroll up to see that too. We say, okay, this Laplace transformation on little f at t gives us some output, some capital F at s, and then minus little f at 0. And where did this all come from? Well, this was the answer that I got when looking at the Laplace transform of f prime at t, which that's what we showed, s times big F at s minus f at 0. So this is, I'll switch to a different color here, but this is equal to the Laplace transformation applied on f prime at t. Sort of squeezed it in there, but that's f prime at t. It's Laplace transform. So that's the first identity we were able to show. Now I want to show that second identity up above. So what we can do, and that involves the Laplace transformation on f double prime, I want to show it's equal to s squared times capital F at s minus s times little f at 0 minus little f prime at 0. But here's what I could do. I could say, let me look at the Laplace transformation applied on f double prime at t, and I'm going to use this relationship that I just showed. So what I'm going to do is I'm going to make the following let statement. I'm going to say, well, let's let f double prime at t be equal to some function g's first derivative at t. And this is just sort of a semantics argument. We think about sort of derivatives in general. Derivatives are functions too. So you could say, well, the second derivative of little f is the first derivative of some function, you know, just to some other function, right? Just like you call your grandmother grandmother and you call your mom mom, but your mom calls your grandmother mom. So grandmas can be moms to someone else too, even though they're your grandma. I don't know if that helps, but I like to get real with things. So I'm going to let g prime take place of f double prime. And if I'm doing this, then it also means that the relationship between g and f is that g at t is f prime at t. So there's something to sort of keep in mind then. I'm going to make this substitution, and I'm going to instead look at the Laplace transformation applied on, I'm going to replace f double prime with g prime at t. And what is this? Well, by definition, this is going to be s times, instead of using this big f at s notation, let me say the Laplace transformation applied on g at t. So I won't quite make the connection to big F yet, but I'll go back to sort of this definition of it. So this would be g at t. And then it's going to be minus, and then since here instead of using, I'm using g prime to talk about this, so this would be little g at 0. So using these two substitutions, replacing f double prime with g prime, and then expanding out, really looking at this idea here, involving that script L notation, but remembering that f should be, I should be thinking about that in terms of g instead, right? I have g prime, and then instead of mentioning f then, I would be mentioning g here. But now that I have this first working version of it, I want to remember, well, okay, g then is actually f prime. So what is this really? If I go and sort of unravel it further, this would be s times the Laplace transformation applied on g at t is really f prime at t, minus, and here g at 0 would really be f prime at 0. Now this is where the magic comes in. I already know what the Laplace transformation at f prime at t is. We showed that earlier, so now I can actually just use that result. So I get s times, and I'll make some parentheses here, minus f prime at 0. But then inside my parentheses, that's s times, this should be the Laplace transformation on f prime at t, which I can now substitute here. That's s times big F at s minus little f at 0. So s times big F at s minus little f at 0 is what we get there. We'd say, well, okay, now let's just expand this out. What does it give me? Here, when I multiply s in, I get s squared times big F at s minus s times little f at 0, and then minus f prime at 0. And this should be equal to what I started with, which is the Laplace transformation applied on f double prime at t. You can show this result with integration by parts as well. It just requires 2 uses of integration by parts. And I don't think it's quite worth it trying to show it that way, since it's a little bit more work, and we can actually use what we already have with relationships between functions and derivatives, and a small substitution to get us there, in order to just unravel it from here. But so now we're saying Laplace transformation applied on f double prime is s squared times big F at s minus s times little f at 0 minus little f prime at 0. And let's see if that's what I was supposed to show. Moment of truth. S squared big F at s minus s times little f at 0 minus f prime at 0. So it follows directly from, if we want it to, follows directly from this first relationship. We just remember, okay, I'm replacing f double prime now with g prime, and then looking at g prime here, I'm getting this relationship in terms of little g at 0 as well, etc., etc. And then from there, I can remember that g is f prime then, sort of keeping that relationship going, and I can unravel all of it. So it looks good. Now we want to remember these results, because what this allows us to do now is to look at a differential equation problem and to use the Laplace transformation to actually solve it. And this is going to be, I think, very interesting to look at. So I hope you enjoy it. But let's go ahead and take a look at it. And since I want to remember these relationships, I'm going to write it up above. But first, we got our table, that same table from the previous lectures there to hang out with us. But I want to take a look at an example. And let me write down what we were saying. Instead of using, for example, f prime and f double prime, let me use x instead, because that's going to coincide a bit better with what we're looking at. So say the Laplace transformation of x prime, and think of this like f prime, if that helps. Well, what was that we showed? We showed that's s times big F at s minus, and then here, instead of little f at 0, we would say x at 0. So s times big F at s minus little x at 0, and that's one of them. And then we also have the Laplace transformation applied on x double prime. And if you remember, this was s squared times big F at s minus s times, I'm going to say x at 0 minus x prime at 0. So here I'm just replacing little f with x is essentially the idea. So Laplace transformation on the second derivative, and we have that one here, s squared times big F at s minus s times, here I'm using little x at 0 minus x prime at 0. And if you don't want to use big F, some other notation that we typically see is a capital X at s, but I'm not going to really worry too much about it, since essentially I'm using these ideas interchangeably, that x is equal to little f at t anyways. So I'll make those substitutions where I think it's going to matter the most, and you could change if you want to. So if you like, if you're a real big stickler for notation out there, then I think sometimes we see capital F at s sort of denoted with a capital X at s in some texts or publications, and that's fine. I just don't think it's quite as necessary for what we're going to be doing. Tomato, tomato, potato, potato. All right, let's see what we get. Let's work with this now. So how can we use these new identities to help us solve a Laplace transformation, to use a Laplace transformation to help us solve an initial value problem? Well, the idea is, if I have this differential equation, I want to apply the Laplace transformation to both sides. So apply it to the left and then apply it to the right. Now I can use linearity. So I know this is a linear transformation, so I can split this up into a sum and I can bring coefficients out. We saw that last time. So Laplace transformation of x double prime plus 4 times the Laplace transformation applied on x equals, now the Laplace transformation applied on the function 0 we haven't talked about yet, but this is going to give us 0, and I want to show why. Of course I want to show why. I'm a math instructor. The Laplace transformation applied to the function 0, by definition, is the improper integral from 0 to infinity of e to the minus st times my function, and here my function is 0. Now if my function is 0 and I multiply the exponential function to it, this is going to give me the improper integral from 0 to infinity of 0 with respect to t. Now if I integrate 0, it gives me a constant. But since this is a bounded integral, this gives me a constant, then I have to evaluate as t goes from 0 to infinity. Since there's nowhere to plug in the constant, and here I can sort of show the idea, it gives me some constant, and it's from 0 to infinity, but it's the same result for any definite integral from a to b. I just get c minus c anyways, since there's no mention of t, no mention of my variable, anywhere to plug in 0 or to plug in a dummy variable and then to take a limit of. So it just gives me 0 anyways. So the bounded integral of 0 with respect to t gives us 0. I think a lot of times when I mention this, someone says, well, isn't it supposed to be a constant? Yes, but we're taking a look at a bounded integral as the idea, and there's nowhere to plug in the upper bound or the lower bound. So when I try to do that evaluation, thinking about the fundamental theorem of calculus part 2, it just gives me 0 out anyways. I just get whatever that constant is minus itself. The bounds don't really get a chance to shine because there's nowhere to plug them in. So it's like, well, I have them, but what do I do with them? Nothing really. So it just gives me a constant, and evaluating that constant, there's no net change there, right? So we just get 0. So Laplace transformation applied on 0 gives me 0. Certainly makes things a lot easier. Now I use these identities next. So Laplace transformation of x double prime, we know that's going to give us s squared times big F at s minus s times little f. Well, here I'm using x's, so let me stick to my decisions here. But you can use little f2 if you want. Does it matter? Not really. I think since we have these given in terms of x, makes it a little bit quicker to say what's going to happen next. Minus x prime at 0, which is what I said here. And then plus 4 times. Now I didn't write it down above, but the Laplace transformation of x is just big F at s. So this isn't for x prime or x double prime. We're just going to say the Laplace transformation applied on the function x, where x is f at t, just gives us big F of s equals 0. And sort of coming from this idea here, that if x is equal to f at t, Laplace transformation applied on x is the Laplace transformation applied on f at t, just gives us an output, some function big F of variable s, and then equals 0. Now what do I want to do next? I have initial values given, so I can plug them in for x at 0 and x prime at 0. So let me rewrite the rest. S squared big F at s minus s times minus, and then x prime will go there, and then plus 4 times big F at s equals 0. But what is x at 0 and x prime at 0? X at 0 is 5. So right here, x at 0, so minus s times 5. And then minus x prime at 0 is 0. So I just substitute those in. Now what do I want to do from here? I want to clean this up, pointing right at you. I want to clean it up, and I want to solve for big F at s. And you'll see why. This is going to tie directly into what we did last lecture. So I want to try to solve. So here, first of all, I don't need this minus 0. It's not doing anything. This negative s times 5, I want to add it to both sides. So I have s squared times big F at s. I'm going to keep it on the left. 4 times big F at s. I'm going to keep it on the left. Equals, if I add this over, I have 5s. on the right-hand side now. And the 0 I don't even need. Now I can factor on the left. I can factor capital F of s out, and I'm left with s squared plus 4, in parentheses, equals 5s. Now, I'm still doing the finger motions. It's important when you do this, when you're doing this on the homework, I want to make sure you wave your finger too when you're thinking about it. It's important for the Laplace transformation. So I want to solve for big F at s. So I just divide by s squared plus 4. I get 5s divided by s squared plus 4. Now what we're going to do, we're going to say, well, hold on. This isn't the solution yet. I want to apply, I apologize for the finger. I'm going to stop pointing and put the finger away. We want to solve for the function of t. So this is where we're going to take a look at our table and use the inverse Laplace transformation. I need my hand back to right, but I'm going to try to lay off the finger wagging. So here's what I'm going to do. I'm going to take this, I'm going to rewrite it ever so slightly, because I've seen a lot of Laplace transformations. Maybe we're still getting comfortable with them, but I think I've seen this one before. I'm going to bring the 5 out times, now I have s over s squared plus 4, but here I'm going to think of 4 like 2 squared. Now the 5 is just a coefficient, so that really shouldn't be what I'm focusing on too much when I'm thinking about the inverse Laplace transformation. But I'm sort of looking at this s over s squared plus 2 squared. Do you remember that from last time? Maybe you do, maybe you don't. We got this table to help us out. There it is. S over s squared plus a squared will map us back to cosine of at. So what that means is if I apply Laplace inverse on this, here I could actually throw it in there if I want to be really strict with my notation, throw it in there. This is going to spit out 5 times cosine of at, and a is 2, cosine of 2t. And this is my solution to the differential equation. So this is equal to x at t. And this is something really amazing. We were able to use Laplace transformations to solve an initial value problem. How would that process look before? Well, we would probably use the characteristic equation. If it's something that's non-homogeneous, we would use the method of undetermined coefficients. We would then get a solution, build the general solution, then work with the initial values to solve for the constants. This already takes into account the initial values and builds the particular solution right away immediately. So that I think is really cool, that we know that now the function x is 5 cosine of 2t is such that the second derivative plus 4 times that function gives me 0 and meets the description of these two initial values. So it's sort of this inclusive all-in-one way of solving where I'm taking everything into account. I'm not really getting a general solution. I'm going immediately to the particular solution. Now, I hear a lot of people mention that this is very interesting because it turns a differential equation into essentially an algebra problem, where here I solve for big F at s and then I use a table to work backwards. I don't like calling it that because there is a lot of calculus here. Just the calculus is all in the framework. The calculus is in building and understanding these two definitions here. So if we want to say that it's void of calculus, I don't really believe that because there's a lot of calculus at the foundation of it. But if we're comfortable with what the Laplace transformation does and perhaps relying on a table, and I don't want you to rely on the table entirely. I want you to start to become familiar with the information on the table to where maybe most of the time you don't even have to look at it. If we are comfortable with that, then we could kind of say, okay, well, I'm not really performing the calculus, but the calculus is there. Make no mistake about it. The calculus is definitely there. But I think it is an interesting way to solve an initial value problem. All right, well, here I have a space for notes. I had blank extra page in case I needed it. Notes. Very cool. We got another problem here. So not a bad idea to write down those definitions again that we're going to be using so we can try to remember them. Laplace transformation applied on x prime. What do we say this was? This was s times big f at s minus little x at 0. The more that we write this down, I don't have to flip all the way back up a few pages of the PDF, to do it. But the more I write it down, also, the easier it is to remember it, because I want to commit these to memory. Laplace transformation of x double prime, this was s squared times big f at s minus s times little x. I'm using x's, I promise you, I'm using x's. Though it doesn't really matter. Minus s times x at 0 minus x prime at 0. There we go. So, yeah, let's take a look at it. So you got another differential equation, and you can toss both sides into the Laplace transformation. Let me use yellow. I don't mean to start and stop so much, but I definitely like using my color coding. I think it makes the lecture a little bit better. Let me know what you think about the color choices. It's a little bit late in the semester to scrutinize, but let me know what you think about the color choices. I like yellow for the bulk of the work. I don't know if you've noticed. That's because it reminds me of chalk. I usually use yellow chalk. Fun fact, I usually use yellow chalk over white chalk, but I got the white chalk for the problems and then the yellow chalk for the annotation. So best of both worlds, huh? Linearity of the transformation, I can break this up into a Laplace transformation of x double prime minus you get a Laplace transformation on x prime minus bring the coefficient 2 out, we get a Laplace transformation on x equals, and we showed and discussed last time the Laplace transformation applied on 0 is 0. So I can just do that. Now let's use those substitutions, those definitions. Laplace transformation of x double prime is s squared times big F at s minus s times x at 0 minus x prime at 0. And then Laplace transformation on x prime, I remember this, but I have this minus sign in front of it, so make sure you're distributing that minus sign in. So minus s times big F at s, but then it's going to be minus a negative or plus little x at 0. So I'm actually distributing, because this is going to become two terms. It looks kind of funny to show this here because it's just one thing. When I substitute it, it's two things. So I get minus s, big F at s, and then minus a negative becomes plus x at 0. And then minus 2 times Laplace transformation on x is just what we're calling big F at s, and then equals 0. So we're looking at all of it right now. Now I want to start substituting those initial values. X at 0 is 0, x prime at 0 is 2. So what do I get? I get s squared times big F at s minus, here s times x at 0 is s times 0, so that's 0, minus x prime at 0 is 2, minus s times big F at s plus x at 0 is 0, and then I can write the rest, minus 2 times big F at s equals 0. Same idea from before where I want to solve for big F at s. So any term that has big F at s in it, I'm going to leave it on the left. So that's s squared big F at s minus s times big F at s minus 2 times big F at s. And then equals, I want to move anything else over to the other side. 0 I don't have to worry about. 0 I don't have to worry about. I wrote this down, I wrote this down, I wrote this down. So it's just this minus 2. I want to add it over. So I get equals 2. Now I want to factor big F at s out on the left. And that leaves behind s squared minus s minus 2, and then equals 2. Okay, now we solve for big F at s. So big F at s equals 2 divided by s squared minus s minus 2. And I want to look at this a little bit more in depth. But so this is where I am now. This is not a solution yet. Got to keep working with it, but almost to a good spot with this. So what I want to do is I want to, if possible, factor this denominator. And it's going to factor, so I'm going to say 2 divided by, I can get my parentheses here, we got s and s, multiplies to -2, adds to -1, so that's going to be -2 and then +1. I'm going to need to use partial fraction decomposition. So, oh yeah, do the little partial fraction decomposition dance. Because it's always an exciting time when we get to use partial fraction decomposition. And what can I say? Probably get used to it, because we're going to have to use partial fraction decomposition quite a bit with this material that we're looking at right now. But that's okay, because we love partial fraction decomposition. Nothing is more fun from Calc 2 than partial fraction decomposition, except for maybe series. Series are a lot of fun too. A lot of Calc 2 information in the entire course, what can I say? But what's nice is that this is a case 1, partial fraction decomposition, and I can break this up into the sum of 2 fractions, some constant a over s minus 2, plus some constant b over s plus 1. Now, pray tell, what from here, you might say? Build the common denominator back. Build the common denominator back. Build the common denominator back. So multiply the first fraction by s plus 1 over s plus 1. Multiply the second fraction by s minus 2 over s minus 2. Now from here, we're going to notice that we get 2 fractions equal with the same denominator. So let me just write that down kind of small in the small bit of space I have here. That's 2 over s minus 2 times s plus 1. Let me know if you like my dance moves too from earlier. Here in the denominator, I have that same common denominator, s minus 2, s plus 1. And here in the top, we have a times s plus 1 plus b times s minus 2. Now, if these two things are equal, which allegedly they are, and they have the same denominator already, then the numerators must be equal. So this really means that 2 must be equal to a times s plus 1, which I can expand that out, a times s plus a, plus b times s minus 2b. And keep in mind that over here on the left-hand side, there's no s term. So we can turn this into a system of equations to work with. So what are my coefficients on s on the right? That's as plus bs, right? Feels like bs, doesn't it? And there's 0s on the left. So 0 must be equal to a plus b, the coefficients on s on the right. Well, what about constants? Well, my constants on the left, I just have a 2, and my constants on the right, so this is not underlined, is a minus 2b. And this gives me a system of equations, 2 equations, 2 unknowns that I can work with. Sorry about that. 2 equations, 2 unknowns. So what can I do? Well, let's get a substitution statement. So if 0 is equal to a plus b, that means b is equal to negative a. And if I plug that into the second equation, we get 2 is equal to a minus 2 times negative a. Or this is really 2 equals a plus 2a, which is 3a. So then a is equal to 2/3. And of course, b is negative a, so I kind of know what b is as well. b is negative 2/3. Now what I can do, I can go back to, in blue, we had our partial fraction decomposition. And I like to think about this as, I like to maybe bring a out in front and b out in front. So I'm going to say a times 1 over s minus 2 plus b times 1 over s plus 1. So bringing a out, 1 over s minus 2, bringing b out, and sort of ignore the stuff in the pink, and b times 1 over s plus 1. And now I know what these are, so I can actually return back to my yellow chalk now. So we'd say a was 2/3. So this is 2/3 times 1 over s minus 2. And then minus 2/3 times 1 over s plus 1. And this is, just by partial fraction decomposition, the same as what we had for big f at s before. Just now it's written in terms of these two smaller fractions. So this is big f at s. So what do I want to do? I want to now apply the inverse Laplace transformation. So I want Laplace inverse applied on 2/3 times 1 over s minus 2 minus 2/3 times 1 over s plus 1. And if we're thinking about linearity of the transformation, I think that's enough. We know what's going to happen with the coefficients, so maybe we can go through this a little bit quicker at this stage. But we say 2/3 is a coefficient. That's going to come along for the ride. What is the inverse Laplace transformation of 1 over s minus 2? Well, maybe you remember this one, maybe you don't. It's going to be e to the 2t. And this is that 1 over s minus a form. Let's go to our table. Where was the table? Here was, well, it's all the way back here. E to the at, 1 over s minus a, maps us back to e to the at. So I'll put sort of a little note to myself here. 1 over s minus a maps us to e to the at. All right, back to the yellow. And then minus 2/3. Well, then what about 1 over s plus 1? This one's a little tricky to see, but it is the same form. Just think about this perhaps more like 1 over s minus negative 1 is the trick. So trying to be sort of flexible, a bit of problem solving, this is going to be e to the minus t. So e to the minus 1 times t is 1 over s minus negative 1, which is 1 over s plus 1. And this is, if I want to leave it like this, or if I want to factor a 2/3 out, that seems like a cool thing to do, e to the 2t minus e to the minus t with that 2/3 factored in front. This is equal to x, our function of t, and is our solution to the differential equation. To the initial value problem, I should say. So now we have a particular solution right away. It just took a little bit of working with these identities and Laplace transformations. So this would be our final answer. Let's take a look at another one. I'll stay with the yellow chalk. So what I want to do is I want to apply the Laplace transformation to both sides. So Laplace transformation on x double prime plus x equals Laplace transformation applied on, notice I don't have 0 anymore, I have sine of 2t. Now on the left, I want to use linearity, so Laplace transformation applied on x double prime plus Laplace transformation applied on x equals Laplace transformation applied on sine at 2t, and let's talk about that in the next step. That's certainly something we have to talk about. On the left-hand side, I want to use those identities. So hopefully we're starting to remember them. Laplace transformation on x double prime, that's s squared times big F at s minus s times x at 0 minus x prime at 0, and then plus, now there's no x prime, so here the Laplace transformation just applied on x is big F at s equals, now I need the Laplace transformation applied on sine of 2t. And let me know if you remember what that is. Maybe pause the video, think about it a bit. Try to do it without that table, but if you need the table, it's still kind of new material, so I think that's fair as well. The Laplace transformation applied on sine at 2t should give us 2 divided by s squared plus 2 squared. And here we're using sine of at gives us a over s squared plus a squared. And let's go back to the table, because I think it's important to see it to make sure that I'm not just lying, like I usually am. Just kidding. Sine of at is a over s squared plus a squared, and we had sine of 2t, so we said 2 over s squared plus 2 squared. Yes. So it looks good to me. Now I want to substitute in my initial values. This is my favorite though, since x at 0 and x prime at 0 are both 0, which means this is going to cancel, and this is going to, it's just 0, so just doesn't need to be there. So I'm left with s squared times big F at s plus big F at s equals 2 divided by s squared plus 4. Now, what are we doing? We're solving for big F at s. So let me factor big F at s out. And I'm left with s squared plus 1 equals 2 divided by s squared plus 4. And to solve for big F at s, I just want to divide. So let me write that over here. Big F at s. Now I have 2 divided by, and s squared plus 4 is already in the denominator. But I'm going to divide by s squared plus 1, so that's going to be in the denominator as well. And this is my function big F at s. Now, I'm going to lean in real close. I want you to know partial fraction decomposition. So we got another partial fraction decomposition to consider. Let's switch to the baby blue. Now I want to know, can I factor these anymore in the denominator? The answer is no. I cannot factor s squared plus 4. If it was s squared minus 4, yeah, but it's not. And s squared plus 1, I can't factor it. So these are irreducible quadratics. I can't factor them anymore, and there's a different approach we would take with the partial fraction decomposition from Calc 2. So this is what we would refer to as a case 3 partial fraction decomposition with these irreducible quadratics. And I'm going to get one fraction for each of these. Oh, let me leave a little bit extra space, actually. Yeah. So I'm going to get one fraction for each of these. And each of them is going to have the irreducible quadratic in the bottom, so s squared plus 4 for the first fraction, and s squared plus 1 for the denominator on the second fraction. And in the numerator, I need a linear term on s. So for the first fraction, I want as plus b. For the second fraction, I really want sort of the same thing, so that's going to be cs plus d. And just keeping that degree off by 1 between the numerator and denominator in favor of higher degree being in the denominator. From here, though, it's really the same mentality as any partial fraction decomposition. I'd like to get a system of equations to work with, and I really do that by building back that common denominator. So this first fraction, I should multiply by s squared plus 1 over s squared plus 1. For the second fraction, I should multiply by s squared plus 4 over s squared plus 4. And we'll sort of jump ahead with this because we can see I'm going to have that common denominator on the right, same as the denominator on the left. So really, we're setting those numerators equal. So 2 is equal to as plus b times s squared plus 1, use parentheses, plus cs plus d times s squared plus 4. Now I want to expand this out as best as I can. So here we have 2 equals, I get as times s squared is as cubed. I get b times s squared is bs squared. I get as times 1 is as. I get b times 1 is b. And then foiling over here, cs times s squared is cs cubed. And then I get d times s squared is ds squared. I get cs times 4 is 4cs, and I get d times 4 is 4d. Now from this, I can build a system of equations. So let's start with the s cubed terms. On the right, I have as cubed, and I have cs cubed. But on the left, I have no s cubed. I have 0 s cubed. So 0 s cubed on the left, 0, should be equal to a plus c from the as cubed plus cs cubed on the right. Think about putting these two terms next to each other, factoring the s cubed out, and setting like coefficients equal, that coefficient on the left being 0 since it's missing. Green. Let's do s squared. Now here on the right we have bs squared and ds squared, and over on the left we have no s squared. So very similarly, 0 s squared should be equal to b plus d on s squared. Okay, all right, let's talk about s to the first. So as and 4cs on the right, there's no s on the left, so that should be 0 on 0s equals a plus 4c times s on the right. And purple, for anything that's not underlined, we have constant on the left is 2 equals, on the right, b plus 4d. And this is our system of equations, very colorful, but we have 4 equations for unknowns. Now what I want to do, let me do green. I already did green. Let me do red. What I want to do is I want to solve the system of equations. Substitution method is great. You'll have a lot of success with that. I'm going to do the elimination method. And let me explain what I'm doing. I'm going to subtract the equations from one another. Let me subtract backwards. This, you wouldn't write it this way if you were actually subtracting, but just for the sake of expediency, let me subtract upwards. And it doesn't make a difference, right? 0 minus 0 gives me 0 equals a minus a gives me 0. 4c minus c gives me 3c. And what does this mean? Well, if 0 is equal to 3c, that means c is 0. And in this first equation, if 0 is equal to a plus c, then 0 is equal to a plus 0, so then a must be 0. And let's go to this other equation. Let me do that same thing. It's very strange, but I would prefer to subtract upwards. I didn't write them in that order, so just bear with me. 2 minus 0 gives me 2, equals b minus b is gone. 4d minus d is 3d. And this means then that d is equal to 2/3. And if I look at this other equation, that 0 is equal to b plus d, well, that means then that b is equal to negative d, so b is equal to negative 2/3. So now I have my constants. A is 0, c is 0, b is negative 2/3, d is positive 2/3. And let's go back to what that partial fraction decomposition was. That was just here in the blue. Don't mind the pink. That was to get that common denominator back to build the system of equations. But that was as plus b over s squared plus 4 plus cs plus d over s squared plus 1. Remember this stuff? And then now I can go ahead and make my substitution. So let me return back to the yellow. We said a and c are both 0. So if those are 0, then it's actually going to kill. Well, that looks kind of offensive. So if that's a 0 and this is a 0, then those s terms aren't actually going to stick around. And this really just becomes b over s squared plus 4, or that's negative 2/3 over s squared plus 4, plus d was 2/3, so plus 2/3 over s squared plus 1. Okay, and that this is my big f at s with its partial fraction decomposition. Now, I don't really love having these fractions in the numerator, so I'm just going to bring those out in front as coefficients and say negative 2/3 times 1 over s squared plus 4 plus 2/3 times 1 over s squared plus 1 equals big F at s. And these actually look pretty familiar. Right? If we're thinking about that table, maybe we're recognizing it. Let me write it this way. Maybe we'll start to see it a little bit better. So big F at s equals here I have 2/3 times, I can think of this like 1 over s squared plus 1 squared. And interesting to think that over here in this first term, I don't know if you're thinking what I'm thinking, I hope you are, I could say s squared plus 2 squared for 4, and instead of just leaving that 1 on top, I could actually take this 2 from the negative 2/3 and borrow it and just put it into the numerator. Safe and sound, right? 2, and then I have a negative 1/3 in front. Just bring that little 2, keep the minus sign, and just sort of swap these out. Now this looks an awful lot like sine of AT. Right, did we say that earlier? Well, we did use it, but let's go all the way back through the neon notes to the table. Sine of AT maps us to a over s squared plus a squared, so Laplace inverse will return us back to sine of AT. And that's what we're looking at here, just 2 instances of it. All right, so where were we? Here we were. So then if I apply Laplace inverse to this negative 1/3 s over s squared plus 2 squared plus 2/3 times 1 over s squared plus 1 squared, then this is going to give me my function, little f at t or little x at t, back out however you want to call it. Let me call it little x at t since I've been doing that. But this gives me negative 1/3 times, this is sine of 2t, notice a is 2, sine of 2t, plus 2/3 times, and this is sine of 1t, or just sine of t. And there we have our particular solution, solved using those Laplace transformation identities. Really cool stuff. Let's take a look at one more example just to make sure that it's real. So let's work here with our differential equation. I like those initial values right away. Laplace transformation applied on x double prime plus 4x prime plus 3x equals Laplace transformation applied on 1. So I don't have a 0 over there on the right-hand side. So I'm working with what I'm working with. If I use linearity, Laplace transformation of x double prime plus 4 times Laplace transformation on x prime plus 3 times Laplace transformation applied on x equals Laplace transformation applied on 1. And feel free to pause the video and try to do this one on your own. I think that's the best way to go through these lectures, is to be working sort of maybe ahead once you feel comfortable and to try it out and then resume the video. But let's keep going here. Using those identities, we would say, well, this is s squared times big f at s, and then minus s times x at 0 minus x prime at 0. Here I have 4 times the Laplace transformation on x prime. So I'm going to think about distributing that 4 in as I'm working, but that's 4 times s times big f at s, and then minus 4 times x at 0. So I'm bringing that 4 in to the familiar identity, and plus 3 times Laplace transformation on x is big f at s equals Laplace transformation applied on 1. Now we showed this in the very first lecture for the section, for the chapter, and this gave us 1 over s. So if you remember that, good. If not, the table's there to help out. And now I'm ready to plug in my initial values. And these are my favorite ones. X at 0 is 0, x prime at 0 is 0, which means they're just going to be gone. See you later. You're a 0. You're a 0. You're a 0. Not nice to say to people in public, but certainly fine to yell at a differential equation with Laplace transformations. So you're a 0, you're a 0. We're left with s squared f at s plus 4s f at s plus 3 big F at s equals 1 over s. And I want to factor big F at s out on the left. Leaves behind s squared plus 4s plus 3, and then equals 1 over s. And I want to solve for big F at s. So big F at s equals, I have 1 divided by s, but then I'm also going to divide by the s squared plus 4s plus 3. Oh, and I hope we're thinking the same thing. Partial fraction decomposition. So let's get working with it. Can I factor that denominator anymore? You bet. You bet. You bet. We got 1 over s. Get a couple parentheses. S and s to start. Multiplies to 3, adds to 4. I think we're thinking s plus 1, s plus 3. Looks good. And this is another case 1 partial fraction decomposition. So this is just going to be my favorite partial fraction decomposition, where I just get these 3 separate fractions, some constant a over s, some constant b over s plus 1, and some constant c over s plus 3. Since we have these distinct linear factors, I get this really nice, probably what we think of when we think of partial fraction decomposition, because it's the nicest. Build back the common denominator. So what is s missing? Well, it's missing s plus 1 and s plus 3, or if I multiply that together, that was s squared plus 4s plus 3. What about b over s plus 1? What is that missing? It's missing s and s plus 3, or that's s squared plus 3s. What about c over s plus 3? What is that missing? Well, it's missing s and s plus 1, or if I multiply that through, that's s squared plus s. Now from here, we just focus on the numerators, since I've built back that common denominator. Get those crayons out of my face. I got 1 equals a times s squared plus 4s plus 3 plus b times s squared plus 3s plus c times s squared plus s, and we expand this out. So I have 1 equals as squared plus 4as plus 3a plus bs squared plus 3bs plus cs squared plus cs, and set those like parts equal. Let's talk about the s squared terms. I got an as squared, a bs squared, and a cs squared on the right, but on the left, 0s squared. I don't see any s squared, so it's got to be a 0. 0 on the 0s squared is equal to a plus b plus c on the s squared terms on the right. What about s? Well, I got 4as, 3bs, cs. What about on the left? I got 0 s's. So that means 0 equals 4a plus 3b plus c. What about constants? Well, interesting. On the left, I have 1. On the right, I just have 3a is the only term that doesn't have some mention of s in it. So this actually gives me something right away. 1 equals 3 times a. I'm just going to jump in and say a then is 1/3. And now that I know this, I can plug into one of the other equations. So let me go to this second equation and plug that in. So 0 equals 4 times a is 1/3 plus 3b plus c, and I can solve for c. So here if I leave c where it is, that means c is equal to, this is a 4/3, so I get negative 4/3 minus 3b. And this is a substitution for me to use in the other equation, the first equation. Keep in mind, though, that a is 1/3, so I get 0 equals 1/3 plus b plus c, but c is negative 4/3 minus 3b. And what is that going to do? Well, wait for it. 0 equals 1/3 minus 4/3 gives me negative 3/3, or that's negative 1. b minus 3b gives me negative 2b. And if I add this over, that means 2b equals negative 1, or that b is negative 1/2. And now that I know b, I can plug back into my substitution to solve for c. So I'm going to do that over here. C is negative 4/3 minus 3 times negative 1/2. So then that means c is equal to negative 4/3 plus 3 over 2. Get a common denominator, so I won't show the work there for this. But if I multiply by 2 over 2, I get negative 8 over 6 plus, if I multiply by 3 over 3, I get 9 over 6. Now these are like fractions, so that means c, 9 over 6 minus 8 over 6 gives me 1 over 6. So c is 1 over 6. And now I know what all those values are. So let's go back to the partial fraction decomposition. In the blue, a over s, b over s plus 1. And then it was c over s plus 3, I believe. Yeah. And now I know what a, b, and c are. I like to think about bringing a, b, and c out of the numerator whenever those values are fractions. So I would say this is equal to, here, what was a? A was 1/3. So I'm just going to drop that in front and say 1/3 times 1 over s. Plus what was b? B was negative 1/2. I'm going to bring that in front times 1 over s plus 1. And then what was c? C was 1 over 6. I'm going to bring that out in front and then 1 over s plus 3. Just so I don't have to look at those complex fractions. I think it looks kind of hideous. And this is big F at s. So what I want to do is I want to take this and throw it into my inverse Laplace. So Laplace inverse applied on 1/3 times 1 over s minus 1/2 times 1 over s plus 1. But if we're thinking, hey, I've seen that before, I think it's maybe better to write it as s minus negative 1, just to preemptively, and then plus 1 over 6 times 1 over s plus 3. Now let's write it as s minus negative 3. And if we remember this one, I'll write it down in red. This is the e, well, not all of them, but most of them, e to the at, remember, maps to 1 over s minus a. So if I want to now run through my inverse Laplace transformation, let's do that. Let's start at the end here. So we have, thought I switched to yellow. Give me yellow. I got 1 over 6, and then 1 over s minus negative 3. That's e to the minus 3t. Here for the middle term, I had negative 1/2, 1 over s minus negative 1. That's e to the negative 1t, or e to the minus t. But what about 1 over s? And maybe we remember that from the beginning of the problem. Remember that Laplace transformation of 1 maps to 1 over s. So in fact, 1 over s through Laplace inverse is going to map back to 1, so I get 1/3 times 1, or that's just really 1/3. And this gives me my function x at t is 1/3 minus 1/2 e to the minus t plus 1/6 e to the minus 3t. And this is my solution to the differential equation, the initial value problem, x double prime plus 4x prime plus 3x equals 1, with initial conditions x at 0 is 0, x prime at 0 is 0. My answer is x is 1/3 minus 1/2 e to the minus t plus 1 over 6 e to the minus 3t. Really cool stuff. What can I say? I think these are some of my favorite problems in the entire course. I want to know what you think about them, though, so definitely let me know on the course discussion board. We got the homework in the homework jar, so please make sure you're taking a look at the homework on our online homework platform. We got some more material coming your way, so there's going to be more of me in this little box doing lectures for you. So I will see you soon, but until then, remember to keep learning, to keep dreaming, and to always follow your heart.